Sine and Fourier sine transforms. Two special versions, but after we study the Fourier cosine, Fourier sine transforms, then we go to the, Fourier transform. Different. Yeah. The most important one is the Fourier transform. Yeah. All right. Introduction first. Yeah. Introduction. Yeah. So at this point, the background knowledge we need to use. Yeah. So we have, two background knowledge we need to use. Yeah. One is Laplace transform, right? Yeah. We have that knowledge. Another is Fourier integrals. Yeah. So here we want to use our understanding of, one is from Laplace transform. Another is Fourier integral. To help us understand this topic. First, an integral transform concept. Yeah, we have the background of Laplace transform, so we can understand this concept easily. Is a transformation in the form of an integral. Yeah, our Laplace transform also in the integral, right? Form of the integral. Yeah. So for integral that produces from given functions to new functions depending on a different variable. Yes. Okay? Yeah. So that's the definition of integral transform. Yeah. So but we have solid background in Laplace transform, so we can understand this concept much better. Yeah. All right. But let's understand a little more. Change the properties of functions by changing the domain of functions. Yeah. So what's the meaning of the sentence? The question, why we want to do this transform, right? Yeah. So you may ask question, why we do this? Right? Yeah. So you need to have some important reason to do this kind of transform. Yeah, the answer is very simple. Yeah. This is the answer. This sentence is the same answer. Yeah, because we want to change the properties. Yeah. Change the properties. Why you want to change the properties? Yeah. Because if we use the older properties, if we do not change, we get stuck. Okay? We don't know how to proceed. Yeah. Older properties. Yeah. Now you make this significant change because this change is big. Yeah. This integral transform change is big. The big change means the property change also big. Yeah. So in your new functions have many completely new properties. Then you can use the new properties, you can do a lot of new things. So that's the idea. Yeah. All right. Change the property of the functions by changing the domain. Here, another concept we need. The domain concept. We change the domain. Yeah. Another important change. The domain is changed. Yeah. What do you mean you change the domain, right? Yeah. This concept, the understanding of this concept. Another important understanding we need to do. Yeah. Of the functions. Yeah. All right. So when I show you some example, then I explain this domain concept. Let us use the Fourier cosine transform as example to understand the change here. Yeah. So what is the Fourier cosine transform? Yeah. Similar to our Fourier integral, right? Yeah. Fourier integral. Yeah. But here, it's different. Yeah. So we define. So from the form, from the form, remember, how do you calculate the capital A of W? Capital A of W, right? Yeah. Slightly different, yeah. But the main part is the same, right? The main part is the same, yeah. But other places slightly different, yeah. So you define, yeah. So you can say you are inspired from the Fourier integral, okay? So you define this Fourier cosine transform by the inspiration from the Fourier cosine integral. Yeah. So you define in this way. Yeah. When you define in this way, you get a completely new function, right? So this f is your original function, f of x, your original function. Now you apply this special integral. Here you can see, if you compare with the Laplace transform, we use the e function here, right? We use the e function, okay? E to the negative sx, right? Okay. We use e function. Yeah. And here you just use a different function. You replace the e function by cosine function. So you get a Fourier cosine transform. Yeah. And after the transform, your function is a completely new function. So we use f c cosine, okay, hat. Yeah, there is a hat on top. Yeah, hat function. Yeah. All right. Yeah. That's the Fourier transform, the special notation for the Fourier transform. This hat notation, yeah, little hat notation. So that's the special notation for the Fourier transform. Yeah. But here we use the cosine version, so we put a little c. Yeah. Later, when we move to the Fourier transform, then we remove that little c. Yeah. All right. So it's a new function. Then domain change. What's the domain change? Yeah. Because your original function, there is a domain, right? The x, there is a domain. Yeah. So the domain, because in the real world applications, when you represent some phenomenon using some function, yeah, so you have some concrete domains in the real world situations. Yeah. So here, let me talk about domain concept in our real world functions representations. Yeah. Some functions, for example, f of x here. What's the meaning of your x, right? Yeah, x is the variable. Yeah. The values you can take for your x variable, we call a domain, right? Yeah. But what is the meaning of your x? In the real world situations, your x could be in different meanings, right? Yeah. Sometimes your x could be time t, okay? Sometimes your x could be position, okay? Coordinates. Yeah. Sometimes your x could be temperature. Yeah. You know, so the meaning of your x could be quite different. Yeah. All right. So the domains, so we have typically there are two types domain, two commonly used, although there are many different domains you can consider. Yeah. One is the spatial domain. Spatial domain. Yeah. X location, okay? That's space information, spatial domain. Another is time domain, time. Yeah. Domains, yeah. All right. Then, after you take Fourier cosine transform on a function, there is an original, older domain. Okay? But after you take the transform, the domain for your W, this variable, completely different. So the domain, you go to a completely different domain. So what's that domain? After you take the transform, so you go to a different domain. Yeah. So usually people call the frequency domain. Frequency domain. So you move to frequency domain. Okay? Yeah. So then, when you do manipulation, yeah. So your data manipulation, this time you are working in the frequency domain. Yeah. So then you can do a lot of different things. Yeah. All right? Yeah. Yeah. And in other words, you can switch between time domain and the frequency domain. Okay? You can switch. Yeah. Sometimes you work in the time domain, sometimes you work in the frequency domain. Yeah. So then you can do much more than before. Okay? Yeah. With this new tool, yeah, you can do much more than before. Yeah. All right. Yeah. The Fourier cosine integral for an even function, so we define Fourier cosine integral, even function. Yeah. Yeah. All right. So the A function, you do comparison. Very similar. Yeah. Very similar. Yeah. Here you can see the only difference is that coefficient. Yeah. That coefficient different, that's not critical. Okay? So this coefficient is not critical. Yeah. Because people do some adjustment on this coefficient. Yeah. Yeah. But other than this coefficient, you can see they are the same. Yeah. Yeah. Here you can see actually this Fourier cosine transform. Yeah. People just change the view slightly. Yeah. Change the view slightly. Yeah. Use the integral transform view to look at the Fourier cosine integral. Yeah. The same thing, but we use a different understanding, different view to see it. Yeah. So we use the integral transform view to see it. All right? Yeah. Yeah. But another thing we can get from the Fourier cosine integral, there are two formulas, right? Yeah. Here, look at the two formulas. One formula is this one, another formula is this one. There are two formulas. Yeah. See, these two formulas, we put together, yeah. Yeah. Then, now we use the integral transform view to see these, to understand these two formulas. Then, one formula corresponds to the Fourier cosine transform. What is the other formula? The second formula. So the first formula corresponds to the Fourier cosine transform. What is the second formula? Second formula corresponds to inverse Fourier transform. Yeah. Think about when we talk about Laplace transform, we also have the inverse Laplace transform, right? Yeah. For any transform, if you do not have the inverse, the corresponding inverse transform, it's useless. Okay? Because when you do the transform from one domain to another domain, you want to come back. Okay? If you do not have the inverse transform, you cannot come back. Okay? So you can only go one way. Yeah. One way. Yeah. So, all right? One-way street. Okay? It's not a two-way street. Because you want to come back. You still want to go back to the original environment of the question. Okay? Yeah. So the inverse transform also very important. Here we have the same situation. So when we do the Fourier cosine transform and we want to get it back to the original function f of x, recover the original function f of x from its Fourier cosine transform. Yeah. You can treat this capital A function as the Fourier cosine transform. Yeah. But the only small difference is at the coefficient. This capital A function, you use pi over 2, but the Fourier cosine transform, you use square root of pi over 2. Yeah. But that difference is not significant. That difference, actually, why people you do that square root power of 2? Because, so for this pi over 2, yeah, because you have one side, you have the transform side, you have the inverse side, and the coefficient at the transform side, you have pi over 2, but coefficient at the inverse transform side, you have 1. It's not balanced, right? Why? When you do the transform, you multiply pi over 2 constant. Why? When you do the inverse transform, you do not multiply the same constant, right? Yeah, so that's something people feel not fair, right? Not balanced, okay? Yeah, not balanced. People want to make the distribution of the resource in a balanced way, okay? Yeah, so then split this pi 2 over pi into two parts. Pi over square root of pi over 2, another square root pi over 2, okay? So one square you put at the transform side, another square root part you put at the inverse transform side. Okay? In that way, you want to make your pair of transforms. Yeah, you have a pair of transform. Yeah. The transform and inverse transform in a nice way. Okay? In a balanced way. Yeah. So you can call. Yeah. All right? Yeah. So the inverse Fourier cosine transform. So we define, so we put the same square root of 2 over pi constant in front of the integral transform formula. See? Yeah. In this way, they have the same constant. Okay? Yeah. So it's a nice pair, right? Yeah. Nice pair. Yeah. Yeah. All right? Yeah. Yeah. That's the Fourier cosine transform. Yeah. Similarly, we understand the Fourier sine transform. Okay? Yeah. 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 From the Fourier sine integral b. Yeah. So we just here you can see we just need to change that constant. Yeah. Using the root of that constant. Yeah. That's spread. Okay. Then we can write the Fourier sine transform directly. Fourier sine mode. Yeah. Yeah. Notation, you use subscript s, that little hat symbol. Yeah. That's the Fourier sine transform. Then inverse Fourier sine transform. Yeah. So in this way. Okay. Yeah. Very nice. Yeah. So you can see, yeah, the Fourier integral we learned in our part B, the previous topic, that's the foundation of our Fourier transform concept. Yeah. All right. Yeah. So other notation, yeah, because after that, remember, similar to our Laplace transform, we have, curly L, right? We use the symbol curly L. So here, Fourier, another big important transform, the curly F notation. Okay? Yeah, F notation. Yeah. Yeah. C, yeah, so Fourier cosine transform F, yeah, we use that. Fourier sine transform, yeah, use that notation. Yeah. And inverse, yeah, inverse we use inverse. Then inverse and original transform, we have, we have that property. Yeah. Yeah. All right. Yeah. So for the transform, inverse transform, we know. Yeah. So this kind of basic properties must be available. Yeah. All right. Yeah. So that's this topic. Next topic, we want to study the properties of these transforms. Linearity property and the derivatives property. Linearity, that's easy. Yeah. And the derivative formula, yeah. Think similar to Laplace transform. We have the linearity property, and we also have the derivative property, right? The Laplace transform. Yeah. So a lot of properties pretty similar, yeah, comparing with the Laplace transform. Yeah. All right. Properties of Fourier cosine and sine transform. Linearity, yeah, very easy. Yeah. Because the definition, you go to the definition, you can see this linearity immediately. Yeah. All right. So both sine, cosine transform, we have this linearity property. Yeah. Then, next, we need to look at the derivative. Yeah. Fourier cosine transform of the derivative function and the Fourier sine transform of the derivative function. Yeah. So we can do some simple calculation. Yeah. Yeah. But we need the conditions. Yeah. So these conditions, yeah. Because when we do integration by parts, we need to use these conditions. Yeah. All right. Yeah, the calculation, yeah, by the definition of Fourier cosine transform definition. Yeah. Then we do integration by parts. Yeah. Yeah. Then the first part we need to use, first term we need to use the given condition. Yeah. Then the second part. Yeah. This second part, can you see something related to Fourier cosine transform, right? Related to Fourier cosine transform. Yeah. Kind of recursion. Yeah. So when you calculate Fourier cosine transform of derivative, the representation, you need to use the Fourier sine transform of that function. Similarly, when you calculate Fourier sine transform of the derivative function, by the definition, integration by parts, yeah, then you need to use the Fourier cosine transform of that function. Yeah. Yeah. Then, yeah, so, yeah, because then you get that. Yeah. All right? Yeah. Pretty straightforward. Yeah. Yeah. Similar to Laplace transform. You have similar formulas. Yeah. Then, just like the Laplace transform, we can calculate the second derivatives. Yeah. 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 Because we do second time, right? So we do derivatives twice. Yeah. So we apply that derivative formula twice. Yeah. The second time. Yeah. All right. Yeah. So that's the formula. Yeah. The twice. But here we can verify it. We prove it. We can prove it easily. Yeah. All right. So we need to use the first derivative formula. Yeah. Yeah. All right. Then we apply the first derivative formula the first time. Yeah. Then second time. Okay? Yeah. Second time. Yeah. The second time, yeah. So you place that. Yeah. After simplification, you get that. Okay? Second one. Then Fourier sine transform, second derivative, the first time. Okay? There, the second time. Yeah. So then you get that. Yeah. So very easy. Yeah. The second derivative. Yeah. All right. Then let's do example. Calculate Fourier cosine transform. Yeah. All right. Find the Fourier cosine transform of the special function. Yeah. Special function. Yeah. here, we want to, so when we do the Fourier cosine transform, so we want to see how hard to calculate, right? Yeah. How hard to calculate the Fourier cosine transform. Yeah. And here, for this simple example, when we calculate the Fourier cosine transform, basically you have two ways, right? Yeah. So you have two ways to calculate. One way, the definition way, or direct way, because you plug in, you use the definition, you have the concrete function, so you plug in, so then you do the calculation, direct way. Another way, indirect way, you apply the properties. Here, you apply the special property, the derivative properties. Derivative properties. Okay? Yeah. So here we want to use the second one. Yeah, derivative properties. Yeah. Yeah. Because direct calculation could be very complicated. So the e function, cosine function, integral could be very complicated. Yeah. So here we want to use the derivative properties, and we hope the calculation is not that complicated. Yeah. All right. Yeah. So to do the calculation, we make our observation. The first observation, because when we calculate the second derivative, the e function second derivative is very easy to calculate, right? Yeah. So from this simple observation, we can see, yeah, so here we are going to use this second derivative Fourier cosine transform formula. Yeah. All right. So from this one, we can see we have a squared times f of x equals f double prime. Yeah. That's the special property of this function. Then, can we apply Fourier cosine transform both sides? Left-hand side, when we apply Fourier cosine transform left-hand side, we can use the linearity property, right? Then when we apply the Fourier cosine transform right-hand side, we have this formula. Yeah. Yeah. All right? Yeah. Yeah. So the left-hand side, by linearity property, we take that a squared out. Yeah. Then the right-hand side, we use the formula. Yeah. This is the formula. Okay? So both sides, you have that Fourier cosine transform expression. You can find it easily, right? Yeah. You can solve this equation for Fourier cosine transform expression. That's this one. How about that? Right? Very simple. You can think about if you do the direct calculation, if you use the definition to calculate how hard it is. Yeah. Right? Yeah. Could be very hard. Right? Yeah. Yeah. All right. Yeah. You can try how hard it is. Yeah. Yeah. Oh, yeah. This one may not be that hard because remember we did the calculation before. Yeah. In our before the break time, when we derived that, remember the Laplace integral, right? Yeah, so we did some similar calculation. Yeah, that place. Yeah, so this one similar to that one. Yeah. All right. Yeah. Just give you some idea. Next, then we need to go to our destination because our goal is we want to define Fourier transform. Right? That's our goal. So we do a lot of preparation. The reason we do so much preparation because we have this big important goal. Yeah. How to go to the Fourier transform. From Fourier cosine transform, Fourier sine transform, then we move another big step forward to Fourier transform. But this big step move, we need to go complex way. Complex, okay? Yeah. Because the reason is by this Euler formula, e to the ix equals cosine x plus I times sine x. Okay. Now you have the sine version of the Fourier transform. You have the cosine version of the Fourier transform. You also have the sine version of the. Can you combine these two versions? Then you get a, complex version. Yeah, because this time it's a complex function. Yeah. That is the Fourier transform. You combine. Okay. All right. So let's look at the details. From cosine and sine forms to complex forms. Let us do some calculation. Start from Fourier integral. So that's our Fourier integral function. Fourier integral formula. All right. Now, here A, B formula. So we have. Okay. All right. Then, we replace A function by its integral. So this time we replace. All right. So then, after we factor that FV function out, look at the parts inside the bracket. It's a familiar formula, right? Cosine WV times cosine WX plus sine WV times sine WX. It's a well-known formula. All right, so we're familiar with that. So by that formula, it is cosine of parenthesis WX minus WV. Inside, it's a nice function. A nice function inside. All right. So then, what's next? The question. What to do next? Here, you can see we have a nested integral. Outer integral, inner integral. Inner integral from negative infinity to infinity, but outer integral from 0 to infinity. 1/2 of the axis. Okay? 1/2 of the axis. All right. Then, can we get the other half, the negative half? So here, to get a negative half, remember, to get a negative half, so here, think about right. So cosine. Let's see. Cosine is even function. Cosine is even function. All right. So here, think about this case. Think about the case. F(x) is even function. Think about this case. Okay. If even function, then the other half, the half from negative infinity, that whole integral equals the positive half, right? Yeah. For even function. Because even function multiply even function, still even function. Then, if we recover the negative half, then, because you double it, right? Yeah, you double. Yeah, because you make up the negative half, basically you double the original quantity, then you need to divide it by 2. That's why fx, we can write this version, 1 over 2 pi, but we can extend the outer integral from negative infinity to positive infinity. Yeah, but that is true for this even function. Okay, for that even function. Then, if f is even function, then f function times, because we know sine function is odd, so f function times sine function, it is odd function. Okay, the product of f function and the sine function is odd. It's an odd function. That means the whole integral on that symmetric interval. Yeah, the symmetric, yeah, must be 0. Okay, so the sine part must be 0. If the sine part is 0, we can add the sine term for free, right? Because the whole thing is 0. Can we add the sine part for free? We can add it for free. All right? Yeah? All right. That means f function, we can just add that, yeah, for free. Yeah. Why? Because if you add the sine part, can we put the I there? Yeah? Because the sine part free. Can we multiply that I to the 0 whole thing, then to that add it? Still correct, right? But when we do that, we get an E function. Yeah? But now, you know, so we get this f equals this version, this formula. So that's the way we go to the complex form. So this is the complex form. With this E function, we go to the complex form. Yeah. It's a transformation. Yeah. Transformation, inverse transformation, right? Yeah. It's a transformation, inverse transform. So we will use the integral transformation view to understand this formula. So we can split this formula into 2 formulas. Okay? Yeah. One is the Fourier transform formula. Another is the inverse Fourier transform formula. 2 formulas. We split. Okay? All right. Yeah. C.4. Fourier transform and inverse Fourier transform. Yeah. So that's how we connect. Okay? Yeah. So we need to get inspiration from Fourier cosine transform, Fourier sine transform to get this new transform. Yeah. All right. Fourier transform. Start from the complex Fourier integral. Yeah. Yeah. So from that integral. Yeah. Recall Fourier cosine transform. Yeah. Yeah. All right. Yeah. So now, yeah, that's for the Fourier cosine transform. So there we write, you know, transform version. Yeah. From the Fourier cosine formula, then we write, you know, Fourier cosine transform. Yeah. So this is the, you know, we call the Fourier cosine integral formula. Then we go to the Fourier cosine transform. Okay? Yeah. So that's the how we do the translation. Okay? Yeah, we can treat this step as a special translation step. Now we want to work on this new Fourier complex Fourier integral formula, and we want to get that Fourier complex transform formula. Yeah. All right. Yeah. So, Fourier transform. Yeah. Based on that, so we define Fourier transform. Yeah. F hat. Yeah. That little notation, little hat notation. Yeah. And the coefficient similar to we split. Right. Remember the the split here. Yeah. This time we also do that similar split. Yeah. Root of that split. Okay. All right. Then, yeah. No. Yeah. So the short notation, simple short notation is that curly f. Yeah. Inverse Fourier transform. Yeah. Similar. The definition. Yeah. You can see the E function, you need to use that I. Yeah. If you do not use I, like a Laplace transform, right? Look at that. Yeah. Yeah. We don't use that I. Yeah. Similar to Laplace transform. But the difference from Laplace transform to Fourier, you need to add that I. Yeah. Yeah. But there is a negative sign. Okay. The transform, you have this negative sign. For the inverse transform, you do not have the negative sign. Yeah. Okay. Yeah. Slightly different. Yeah. Yeah. So it's because in this way you do not treat as the same transform, right? Yeah. Inverse and original transform should be different. Should be different. Yeah. Yeah. But the difference you can see very little. Yeah. Only a sign change. So you change from the transform to the inverse transform. Yeah. So after this definition, then we can study the properties of Fourier transform. Yeah. Properties of Fourier transform. Yeah. All right. So let me leave the property part next time. Yeah. So we after that, yeah. So next week, yeah, we have. Next week we will another important topic. Yeah. After we learn the Fourier transform, another important topic we will learn, that's the fast Fourier transform. In engineering, this topic is very important. Fast Fourier transform. So I want to use one whole class to study the fast Fourier transform. Why we can do fast Fourier transform that fast? Okay, I will explain the algorithm of fast Fourier transform. Yeah. Because later you can use software, so you do not need to calculate fast Fourier transform directly, because in many software, so you have built-in fast Fourier transform. You can use directly, but you want to understand the algorithm, the whole idea of the algorithm. Okay, yeah. Before you apply that fast Fourier transform. Yeah. All right, so that's it.